How does a database guarantee that the execution of its transactions is correct? How does it guarantee that transactions execute in a serializable schedule? What are database locks and how are they used? What are the different kinds of database locks? And why do we need many different kinds? What is two-phase locking? What is it needed for? And what are its limitations? If you want to know the answer to all these questions, let's dive in together. Hello and welcome. My name is Elhelw. Today we are going to continue talking about transactions. Specifically, we're going to talk about concurrency control. Concurrency control just means how to control the execution of multiple transactions to ensure, consistency and correctness and so on. In the last video, we talked about schedules. Schedule is basically an ordering of the operations in one or more transactions that basically mirrors or shows how these transactions are executed. And for any given number of transactions, there can be many possible schedules depending on how the interleaving happens between these transactions. Some of these schedules can produce correct results and preserve consistency and so on, while some of them may not be correct. We also talked about schedules in the context of both recoverability as well as serializability. For serializability specifically, we saw that we can talk about schedules in the sense that we have serial schedules. The serial schedule is basically a schedule where one transaction will execute from start to end, not interrupted by any other transactions, and then another transaction will execute from start to end, and so on. So basically, there is no concurrency in such a schedule, but this kind of schedule is guaranteed to be correct. To try to relax things a little bit and introduce concurrency and introduce interleaving, we talked about a class of schedules called serializable schedules. These are schedules where there is concurrency and there is interleaving between the transactions, but the effect of such a schedule is as if the transactions are executing in a serial manner. So such schedules also produce correct results while allowing for better concurrency, which means better resource utilization, better throughput, and so on. We also saw how to figure out if a schedule is serializable or not. We used a dependency graph, and we saw if there are cycles in this graph, then this schedule is not serializable, and so on. I will put a link to that video in the description as well as up on the screen, so please feel free to watch it if you haven't already, because it will make it much easier to follow along with this video. So regarding that last point, regarding checking whether a schedule is serializable or not, obviously as a database system, it wants its schedules or it wants the transactions to execute in a serializable schedule. But it cannot wait until the schedule is done in order to figure out if it was serializable or not. Because in order to use the dependency graph method that we talked about last video, we basically need to wait until we have all the schedule done and we know the order of the operations, then we can construct that dependency graph. So clearly this is not something that the database can do. So we need to find a different way to check, or to even not check, but to enforce. So in practice, databases don't use this method. They use other methods to basically avoid having a non-serializable schedule in the first place. So there can be some rules, there can be some techniques that the database system can use in order to force the execution to happen in a serializable schedule. One such way to enforce this is using locks, database locks. What are database locks? These are mechanisms that we use in order to limit the interference between transactions. Basically, a lock is something where you have two operations, lock and unlock. If you're familiar with mutexes, or if you're familiar with other similar constructs like latches and so on in operating systems, this is something similar where you put the lock instruction before the critical section, and then you put an unlock after the critical section. And then if two transactions, if one of them already acquired the lock and if another one wants to acquire a lock, then it will be blocked. It will have to wait until the first transaction releases the lock, and so on. So this is the broad idea of using locks to try to limit the interference, or to try to limit access to certain parts, whatever objects are being read or written by a transaction. So in the very simple sense, let's say we have a transaction that looks like this. It has a begin, it has a commit, and then in the middle it has a read and a write X. So what we want is we want to limit that access to the object X as it's being read and written. One way to do this is by adding a lock X in the beginning and then unlock X at the end. So this means that this basically is the critical section for this transaction, and you put a lock at the beginning and then you release that lock at the end. So let's say we have two transactions that have this same code. So basically, like, imagine two instances of this function or something are executing at the same time. Let's see what the interaction between them would look like, or what the timeline would look like. So let's say T1 starts first. So we have the begin instruction, and then it encounters the lock operation. So this means that T1 will acquire a lock on variable X. Let's put a note by the side that X now is locked by T1. So T1 already acquired a lock on X. T1 will be able to proceed. But let's say that T2 starts. So now we have at the begin from T2, and now we have the lock X instruction from T2. So T2 is attempting to acquire a lock on X as well. However, because X is already locked by T1, then T2 will have to be blocked. So it will have to wait until X is unlocked. So T2 cannot proceed any further. Now it's blocked. T1 can proceed, so we'll have the read X and write X normally, and then we get to the unlock operation. So T1 unlocks X, means that X is no longer locked by T1. This means that T2 can now proceed. So T2 will acquire the lock that it was requesting. So now X is locked by T2, and T2 can also proceed, read X, write X. Eventually T2 will also unlock X, so now X is not locked by anyone anymore. And then T2 and T1 can also both commit. So this is the basic premise of how locks can be used. In this particular example, or in this explanation, we assume that we have just one type of locks. Whether you want to read, whether you want to write, you're just going to lock that object and then unlock it afterwards. In practice, this is not really how things are done, because this limits concurrency to a great extent, especially in the case of multiple reads. If you have multiple transactions, let's say trying to read the same object, and we use the mechanism that we just saw, then only one of them will be able to read it at a time. So basically each one of them will read it in turn, all the others will be waiting. For reading specifically, we don't need to do this, since no one is changing the value. In theory, they could all read it at the same time. Like, you shouldn't care, right? But if we use locks the way we just saw, it will happen in a serial manner. So for that purpose, the next step would be to have two different kinds of locks to deal with the reads and the writes in a different way. The most common types of locks that you probably have heard about or seen in multiple contexts is shared locks, or S locks, also known as read locks. And we have exclusive locks, or X locks, which are also known as write locks. I'll probably be using a mix of the terminology, but I'll try to stick to S lock and X lock to refer to them. But in case I slip and say read lock or write lock, then you still know what I'm talking about. So the S lock, or the shared lock, is usually used for read. So if you want to read something, you use the S lock to lock that item, and then you unlock it at the end. If there are multiple transactions requesting S locks, they can usually all go through, but that's why it's called shared, because it can be shared by multiple transactions. The exclusive lock is something that can only be held by a single transaction, and no one else can access that same object at the same time. So now that we have two types of locks, I kind of went through it, but as a formal way, we need to understand how they interact. So we have this compatibility matrix. So you can think of the rows as, a transaction already holds a lock of a certain type, and the columns meaning that a transaction is requesting, like another transaction is requesting a lock of a certain type. So the only compatible pair is shared lock and shared lock. So if a transaction already holds a shared lock on X, and another transaction is requesting a shared lock on X, it will be granted that lock, and it will also be able to proceed. Any other combination, the requesting transactions will be blocked until that object is released. This specifically helps, as I said, it helps concurrency in the case of multiple reads. So all transactions will be able to proceed if all what they want is to just read the value of a particular variable or a particular row, and so on. Okay, so in practice, it would look something like this. So if you have, let's say, a write and a read operation, one possible way to do the locking would be to do an X lock for the write, and then you unlock that. There might be some other operations in the middle, and then when you need to read, you can do an S lock, do the read operation, and then unlock. Alternatively, you could just do like an X lock in the beginning, do everything that you want, and then do an unlock at the end, because X locks also support both read and write. One of the operations that you can do in the lock is upgrade or downgrade. So like if you have an S lock, you can upgrade it to an X lock. So if you do just X lock, you will be able to do both reading and writing as much as you want. Of course, this means that you hold the lock for a longer period, so this also limits concurrency, so you have to figure out what's the best way to do this. So suppose that we have locking in the way that we see here right now. Let's look at an example with two transactions to see again what the timeline looks like and what the interaction between the locks looks like. So say we have T2 and T1 here, as we can see. This is the timeline. So suppose that T1 starts, so first operation is X lock A. So it will acquire a lock, an exclusive lock. So A is X locked by T1. T1 can still proceed. Suppose T2 starts. Now it also wants to acquire an X lock on A, but because A is already locked by an X lock, and we know that X locks are not compatible with each other, then T2 will have to be blocked and wait until this lock is released. So T2 cannot proceed any further. T1 will go do the right operation, and then it will unlock A. So at this point, A is not locked anymore. So then T2 will be able to proceed and acquire the X lock that it was asking for, and it can keep going. However, assume that control just returned to T1 for some reason, and now it's trying to acquire an S lock or a shared lock on A. Again, A now is locked by T2 using an X lock. S locks and X locks are not compatible, so T1 will have to be blocked and wait. So T1 now cannot proceed any further, but T2 can. So T2 will do the right A, and then it will unlock A. So this means that now T1 can proceed and acquire that S lock that it was requesting, and now T1 can do the read and unlock at the end. So given that exclusive locks and shared locks, we see how they can interact together to prevent two writes happening at the same time, or a read and write happening at the same time. But let's go back to something that we talked about last time. Remember the check for serializability? Is this schedule serializable or not? Let's construct our dependency graph. How do we construct the dependency graph? We look for conflicting operations, and then for each conflicting operation, we add an edge to the graph. So the first pair of conflicting operations is write A in T1 and write A in T2. And because the one in T1 happens first, then we add an edge from T1 to T2 in the graph. We have another pair of conflicting operations, which is the write A in T2 and the read A in T1. And because the T2 one happens first, then we add an edge from T2 to T1 in the graph. Now we see that we have a cycle. Having a cycle means that this is not a serializable schedule. So even though we're using locks, we're using shared locks, we're using exclusive locks, we still cannot guarantee serializability. So we need to do something more than that in order to guarantee serializability. This takes us to something that we call two-phase locking. So two-phase locking is a locking technique or a locking rule that guarantees a serializable schedule. We have a certain rule that we have to apply in terms of where to lock and where to unlock, which guarantees that things will happen in a serializable manner. Two-phase locking, as the name indicates, like I said, it's a locking technique, but it has two distinct phases. Before we get into what these phases mean, let's look again at the previous example. So this is the example that we were looking at. The reason that this was not serializable basically is because of this write operation, right? The fact that this write operation, got there in the middle between the first write and the second read, this is what made this schedule unserializable. If this write happened, like let's say at the very beginning or at the very end, then we will not have a cycle in the dependency graph. Okay, well, if this write operation is the problem, what allowed the write operation to happen at this point in time? The reason it was allowed to happen is because we unlocked T1 after we did the first write, and then we acquired another lock later on when we needed to do the read. So between this unlock and lock, T2 was able to get in and do that write operation. So keep that in mind, and let's look at a simple graph that shows the number of locks being held by a transaction, right? So let's focus on T1. So if the x-axis is the time, right, and the y-axis is the number of locks being held, we can see that in the very beginning, before anything happens, we're not holding any locks. But we then, do or get an exclusive lock on A. So now we're holding one lock. After some point, we unlock A. So basically, we release that lock. We're not holding any locks anymore. And then after some time, we acquire another lock on A, but shared lock this time. And then again, at the end, we release this lock. So if we look at this graph, we'll see ups and downs. Every time we acquire a lock, we go up. Every time we release a lock, we go down. This is basically what caused the dependency in the graph, or what allowed that right to happen. It happened basically in that valley between the two hills in this graph. So this takes us to the two-phase locking technique. As I said, two-phase locking has two distinct phases. The first phase, phase one, we call that the growing phase. In this phase, a transaction is allowed to acquire or upgrade locks as much as it wants. It is not allowed to release or downgrade locks. Upgrade means going from shared to exclusive, right? Downgrade mean to go from exclusive to shared lock. So you can acquire locks, you can acquire S locks, you can acquire X locks, or you can upgrade an S lock to an X lock. Of course, you can also do other operations like reads and writes and whatnot. So all those operations are allowed in the growing phase. We're not allowed to release or downgrade locks. Once we're done with the growing phase, then we move on to the second phase, which is the shrinking phase. The shrinking phase is the opposite. In this phase, we are allowed to release or downgrade locks as much as we want, but we're not allowed to acquire any new locks. So if we look at the graph for two-phase locking, this is what it looks like. Basically, it just goes up during the growing phase. At the end of that, basically, we know that we have acquired all the locks that we need. And again, we can be doing other operations as well. And then at some point, we realize that, okay, we don't need some of these locks anymore, so we can start releasing locks until the end. So there will be an upward trend in the growing phase and then a downward trend in the shrinking phase. The point at which we have all the locks that we need, we call that the lock point. So before that lock point is the growing phase, after that lock point is the shrinking phase. So this is what a two-phase locking timeline looks like for a given transaction. If we look, just to contrast, at this timeline for another transaction, we can see that, valley happening there. This means that we release the lock and then we acquire a new lock. Basically, the first time you release, this means that you are now entering the shrinking phase, right? So once you've entered the shrinking phase, you cannot acquire locks again after that. So if you have something like this, then this means that this is not a valid two-phase locking timeline. So just to, by intuition, you can tell which is which. So if we look at that past transaction again from the last example, you can see that we have this, unlock followed by a lock. So this means that this is not two-phase locking. But if you have something like this, which does just X lock in the beginning, and then all the read and write operations, and then unlock at the end, this is valid two-phase locking because it doesn't, release and then lock something else afterwards. One thing to note, obviously, is that the two-phase locking, it can reduce concurrency because basically we're holding on to locks for longer than we would otherwise. So this means that other transactions would be blocked. They will not be able to interleave as much as they could without two-phase locking. However, it's a sacrifice where we're basically sacrificing some of the concurrency to achieve, better serializability. Also, I wanted to point out something. Remember when we talked about that lock point where we know that we have acquired all the locks that we want? Basically, just an intuition. If you think about multiple transactions doing two-phase locking, right? So each transaction will have a lock point. The transaction that reaches its lock point first, this transaction is able to continue because it's not blocked on anything else. It has all the locks that it needs, and it can just, continue afterwards. And then it will start releasing locks. The transaction that reaches its lock point second is allowed to continue second, and so on. So basically, this means that any group of transactions that are implementing two-phase locking is equivalent to a serial schedule, based on the order of the lock points. So this is why, intuitively, it guarantees serializability. Even though we guarantee serializability, it doesn't mean that the schedule with two-phase locking is, free from problems. There are still other problems that might still be there and we want to fix in different ways. We will talk about one of them today, and then the rest will wait until the next video. So let's see what problem we are talking about here. All right, let's look at this example. So we have two transactions. Both are actually valid two-phase locking. If you look at T1, you'll see that it does, X lock A, X lock B in the beginning. It has some reads and writes. So this is the growing phase, and then it starts the shrinking phase where it does unlock A, write B, and then unlock B. So very distinct two phases here. T2 also it just has one lock that it locks at the beginning and then unlocks near the end. So this is valid two-phase locking. However, we have these two instructions, right? We have a write A at some point in T1 and a read A little bit later in T2. So basically T2 is reading the value of A that was written by T1 before T1 commits. If you remember, what did we call that? We call that a dirty read. When the transaction reads a value that was written by another transaction without being committed. What's the problem with dirty reads? Dirty reads are not always a problem, but in some cases they can be. For example, let's say a failure happens in T1 before it commits, right? So when a failure happens, we need to roll back T1. So T1 is going to be rolled back. Because of the dirty read, it means that T2 now has read a value that actually was rolled back. So T2 also needs to roll back because of that dependency. This is something that we've also mentioned in the last video, and we call that a cascading rollback, which means that when you have to roll back a transaction, and that triggers rolling back, one or more other transactions, even though those other transactions did not have any failures or anything, right? Of course, this cascading rollback is expensive because there's a lot of wasted work. Like, any work that's been done by T2 is now wasted because we have to roll it back. It could also trigger rolling back other transactions and so on. So we try to avoid having cascading rollbacks. And as we can see here, even though we are implementing two-phase locking, we can still have cascading rollbacks. Why did this cascading rollback happen? Because of the dirty read. Well, why did the dirty read happen? The dirty read happened because T1 released the lock on A, which allowed T2 to go and read A before T1 committed. So how do we solve this? We solve this by taking the two-phase locking technique and refining it, coming up with a stricter version of it, which is called strict two-phase locking. Strict two-phase locking says we still have our growing phase and our shrinking phase, but in the shrinking phase, transactions can only release the exclusive locks after they have ended, either committed or rolled back. So it will hold on to all the exclusive locks all the way until the end, and then it will release them. What does this do? If a transaction holds on to all exclusive locks, which means that if it has written anything, then it has an exclusive lock, right? It will not release those locks until the end, until after it commits. So this means that if anyone else is trying to read that value that was just written, they will have to wait until that first transaction commits. So by the time they read it, it will not be a dirty read anymore. It will be a committed value. So then we avoid the dirty read problem and we avoid the cascading rollback. If you remember last time, we talked about cascading rollback in the context of recoverability. We said there is a type of schedules which is called cascadeless schedules that avoids cascading rollback, and then we talked about an even stricter type of schedules called strict schedules. In a strict schedule, basically any write-read or write-write conflict needs to have the commit before the second instruction happens. This is basically what this does. Because we're holding the write locks all the way to the end, so any other transaction that is trying to read or overwrite a value is going to wait until after the commit. So basically, using the strict two-phase locking, we produce strict schedules. So they're serializable and they're also strict. We have an even stronger version of that, which we call the strong strict two-phase locking, or sometimes called the rigorous two-phase locking. Basically, it takes the definition of the strict two-phase locking and says, okay, transactions can only release all the locks after they've committed or rolled back. So not just the exclusive locks, but all the locks. So clearly this is more restrictive than the strict two-phase locking because we're holding on to all the locks much longer. Again, this limits concurrency, but it helps with avoiding cascading rollbacks. The reason this is attractive is because it's easier to implement than the strict two-phase locking, because you don't need to know what kind of locks you want to keep and what kind of locks you can release early. This basically just holds all the locks all the way until the end, and then it releases everything once it's committed or rolled back. So this is easier to implement, which also makes it more common in most systems. And like I said, it provides the guarantee of no cascading rollbacks. If we look at the diagram, this is the diagram of the basic two-phase locking that we've seen before. If we want to look at a similar diagram for the strong, strict two-phase locking, it will look something like this. So again, the growing phase is the same. You're acquiring locks as you go, but then you're not releasing the locks one at a time. All the locks are being held all the way until the end, and then once we reach the end of the transaction, then all the locks are just released at once. So this is an example of what it would look like. Look at T1 here. So you do an X lock A, read A, write A, and then X lock B. You're still in the growing phase. You're acquiring locks, write B, and then it commits. And then after the commit, unlock A and unlock B. So T2 is trying to read A, so it's trying to acquire an S lock on A, but it cannot because A is locked all the way until the end. So it can only acquire that lock after T1 has committed. So the value that it reads is not a dirty read, it's an actually committed value. So then there is no cascading rollback in this case. Like I said, this is a way to avoid cascading rollback. Cascading rollbacks is not the only problem that we still have to solve. So there are other problems. We'll continue talking about these in the next video. One, just to kind of give you a hint of what that would look like. Basically, one of the main and most common problems that still can occur with two-phase locking is the problem of deadlocks. So we're going to continue talking about that in the next video, among other topics. For now, let's summarize what we have talked about today. So today we talked about concurrency control, or we started to talk about concurrency control, which means controlling the execution of multiple concurrent transactions to guarantee consistency and correctness. The first technique that we've talked about is locks. Locks are a mechanism that we use to try to limit the interference between transactions. We talked about simple kinds of locks like shared locks and exclusive locks and how they're used for reading and writing. We also talked about two-phase locking and what it means in terms of the growing phase and the shrinking phase. When can locks be acquired? When can they be released? Two-phase locking guarantees serializability. However, other problems can still occur even if we use two-phase locking. And we talked about one example of such problems today, which is the cascading rollback. And we saw how to solve that problem using the strong, strict two-phase locking technique. And like I said, we're going to continue that topic in the next video. If you have any questions or comments or anything that needs to be clarified, please let me know. I'll try to get to this as soon as I can. Please like the video if you found it useful. Please subscribe to the channel. And with that, thank you so much for following and for watching. And I will see you in the next video.